Hello and welcome to a new episode of the Aerospace Testing International podcast. I'm Ben Sampson, editor of Aerospace Testing International. So, after a couple of months off, we've decided the time is right to start republishing the podcast. Now, what better way to start than by decoding some of the latest trends in aerospace development with Mark Walker, Application Engineering Manager at Mathworks UK. So most people will be familiar with Mathworks. Their MATLAB and SIMULINK are mathematical tools for design and analysis that are used in almost all systems and embedded software development within aerospace at some stage. Think things like developing flight control systems through to modelling and analysing the behaviour of whole aircraft and spacecraft in different environments. Now, Mark works with the company's aerospace and defence clients, helping them make the best use of the software. So I talked to him last week about some of the more recent concepts in aerospace development attached to digitalisation, things like digital twins and model-based engineering. During the talk, we discuss just what these approaches are and how people can start using them effectively within their own development programs. So I hope you enjoy the chat. Morning, Mark. Thank you for your time for this interview. It would be a good place to start if you could just tell me a little bit about Mathworks and what you do at the company, please.
Yeah, so my name's Mark Walker. I'm Application Engineering Manager for Mathworks UK. My work focuses on how our customers, primarily in the aerospace and defence industry, make use of our tools for design purposes, systems and software.
Great. Now, I know Mathworks is a very very feature-rich part of software that's used across lots of different sectors. Could you just describe to me what aerospace engineers would typically be using your software for?
Sure. I think the two main areas are systems and embedded software, but you can think about this more across most design tasks that engineers do. So the underlying thing they're accessing is the mathematical capability in our tools. So it will be for designing things like flight control computers, will be for designing health monitoring systems for different parts of aircraft systems, as well as supporting analysis for other tasks, so mechanical and electrical design are two really common ones.
So do you work with a specific part of the supply chain, or is it everybody?
It is everybody, but we naturally focus more on the airframer end. So it's the sort of blue chip, the large UK aerospace and defence companies primarily.
Okay, and just for the benefit of the listeners who might not know, I mean, what sort of scale are we talking about? Are we, how many companies would be using your software? How many sort of engineers would be using it?
Sure, it's used in a very wide range of companies. So if we could look across the supply chain, and our customer base would be thousands.
Yeah.
If we look at the sort of major design projects, sort of major airframes, big engine programs, big defense programs, it'll tend to be the design teams focused on those programs that are working extensively in our tooling. And so at each organization, that could be teams, that extends to thousands of engineers.
Okay, great. So we did have a quick chat before we started this interview, but one of the things I'd like to discuss here are some of these new concepts that we've got in software development and things to do with digital thread and digital twins and model-based engineering. Just if we could explain some of those and talk about how they might apply to different projects and how they might best be used. So could we start with the idea of a digital twin and a digital thread? I mean, how can they be applied to aerospace development and what sort of potential benefits are we looking at?
Sure, I'll start with the digital twin idea. So this is more at the operational end, but something that you need to start thinking about early. Let's define a digital twin. I suppose the best way to think about it is we develop a model of some kind of asset that we're going to put into service. This model then helps us predict how that asset in service is going to wear out or deteriorate over time. Mm-hmm. It gives us much greater insight into how that asset is operating. Why is that useful? So we can set our service margins, our intervals for when we need to go and maintain that asset. We don't want it's costly to maintain it more than necessary to over process it. But at the same time, these assets are often safety related safety critical things. So we have to be conservative in how we set these service schedules for the parts. And the digital twin can really tell us to only intervene when necessary. We have a much better picture of how that asset is deteriorating.
Okay.
So it's quite an exciting area. It helps us be much smarter with when we need to intervene to do planned maintenance, etc. It's a bit like a more sophisticated version of how you would get your car serviced. It's the same. It is the same idea.
So, I mean, when would you develop a digital twin? Would you do it in your software? And how does it relate to the physical one? You need a physical model as well, or?
Yeah, let's talk about that, because the digital twin can actually contain many different models of how things deteriorate and wear. This is the pretty well-established way of doing things. So I won't necessarily have a model of everything that my asset does, but I will have very specific models of perhaps what I know how that deteriorates. I think a good example would be, just consider a pretty well-established one is if you think about a gas turbine in service on an aircraft wing. It's pretty well established. People have been doing monitoring for the health and condition of that gas turbine for 20, 30 years in some way or other. And modern systems transmit back a lot of data. A sort of the classical way of doing this, the way it's been done for a long time, essentially you listen to it. You listen to the vibrations from it. You can actually infer an awful lot about how it's running from listening to the noise it makes. You can also log other signals, of course. I think there's a good analogy for that sort of just listening and hearing and having that live data. I was reminded of there's an old job that people used to do on the railways where someone would have to go along and hit the wheels of a train and hear what ring they made.
Yeah.
And that was a way of detecting whether they had a crack in them. So it's that same idea that at the core of a digital twin is something that's listening to what's happening in service and using sort of engineering judgment really to decide if it's working correctly or not. But what we're seeing, the exciting bit, is that the way that we build these models that support digital twins, back to what we said earlier, these physical models, it's becoming much, much more sophisticated today. So if we look at modern projects, what the sort of state-of-the-art ones are doing, we're actually building a much, much higher fidelity model of how that, let's say engine, but we could say asset, is going to behave. And that model is constructed in a way that we can actually inject faults into the model and model what the outputs do in the presence of those faults. So we've got this early design model, and this model is also used to support the design process for the engine itself. If we've got this faultable model, what we can do is deliberately inject the faults and learn the difference. And these days, we're actually applying, so we can learn what the outputs look like in the presence of faults. And perhaps one of the more exciting techniques is actually how we can then use that model to train a neural network to learn how to hear the faults. So the analogy is it's like the railwayman's ear, but we're training these days a neural network to listen and be able to classify between normal operation and faulty. And it's these machine learning models that are now placed in service that support that's how the digital twin learns to hear whether the ring sound is good or not. And so this can detect really, really deeply hidden faults in very, very a mass of data and very, very noisy signals. So it's a pretty exciting area supported by modelling.
Okay, sure. And how about earlier on in the kind of testing, particularly in aerospace, where testing and certification is so important? I mean, how are we seeing digital twins used? I mean, would you? I mean, you used the term model there. Are we shying into? There's another term at the moment called model-based engineering that we hear a lot about. Are we shying into that kind of area of model-based engineering with that?
Well, we kind of are, because model's a bit of an overloaded term. Model can actually mean lots of things, from very abstract to very specific. And I think if we were to think about what is model-based engineering, it applies models in many different areas throughout the development process for the asset that you're putting into service. So think about it as I've got models, these mathematical models that are supporting design decisions that I make early on. They're then supporting testing. So a model of how I expect the asset to behave means I can test components, perhaps software components, and how those designs work. a model will tell me about expected behavior on some sort of test rig or some sort of hardware test. And then the final bit that brings all the models together is how these models can be used to support the development of digital twins that we've just been discussing. So that term model for these mathematical models applies throughout the development life cycle, from early concept studies right through to in service. Okay. But I think I should add one more thing as well, which is a second type of model that's used. So I've talked about models of physics, mathematical models of physics. The other way the term model is used is in a description of what something must do. So that's where a model is being used to describe, sometimes just through a picture, sometimes through some more mathematical behavior, a specification, what I expect a thing to do. And commonly when we hear model-based engineering, it's that second part that people are meaning. So it's model-based specification of systems. You can imagine you start at a very abstract level and specify a system down to much more detail. So that's the other big area that our tools are used for, is again a very exciting area in aerospace, and is changing how people are doing things.
Okay, so if I understand that correctly, it's to do with you expect a part, it could be, I think we're going to say turbine engine, I guess, to behave in a certain way, and that's built into the model, right? Is that? Yeah. Okay. Right.
That expected, if I've got that behaviour, that way I think it's going to behave, it supports so many different parts of the design process. And the model, maybe the physics, also though, a really important area is how models are used to specify embedded software that forms part of a modern aircraft. Where modern systems are so reliant on the embedded elements of how control software interacts with, you can imagine, airframe level or at the gas turbine level, how the engine operates. Yeah. So today, software is incredibly coupled to the other disciplines. And so we use models. The models of the software behavior are as important as the models of the physics.
Okay, yeah. So you used the term earlier on, you described, you described a model as having fidelity. I mean, how complex do these models get? I mean, and how much investment in time and money does a company have to put in, does an engineer have to put in before they can start really, getting some benefits from this type of approach?
Yeah, a model can be, we think about this range of fidelity. A simple one from GCSE physics, F equals MA, is something I apply in my working model building work all the time. So that's a very simple equation-based model, and that sits at one end of the spectrum of how we describe what a system's going to do. In that case, that would be, how does the system move? That the amount of physics you include can then increase, and this is how we term increasing the fidelity of a model. So I will then add other behaviors. I may add thermal considerations. I may have much more detail about motion, vibration, flexing in my design, and I can start to add more and more physics in and build a much more complex physical model of the system. At the sort of full detail end, the full physics, or what we call the 3D models, which are things like CFD, the fluid dynamics type models, which also support the development. So you've got this really big range of fidelities. And importantly, you've got the lower fidelity ones are still really useful because they're so fast to run. The higher ones take a long time to give an answer, but a fast answer is sometimes exactly what we need because we can study more cases. I'd like to add as well that the other form of model these days, I talked earlier about how we were using machine learning network to approximate something. The other category of which machine learning is one of them is a statistical model. So we expect, given these inputs, this thing will do roughly this thing. And that's also gives us a valuable result. And typically they're also very fast to run. So I hope you can see in terms of the building models of things, this range of fidelities, that's how they apply.
That's very interesting, Mark. Thank you. I'm just wondering, what kind of role does sort of real world testing play in this model based kind of approach? I mean, presumably the data for the models has to be based on something, right? Absolutely.
So we've got to have confidence in our models, and one of the primary ways we get confidence in a model is that we do a physical test and we compare that to what the model thought the test would conclude and see, do we have agreement? In practice, models contain uncertainty. We will have things where we've approximated, where we've estimated, and we need to produce some evidence to show that our assumptions that we've built into that model are valid. So, of course, test data validating a model is a really, really important thing where the world of test and the world of models comes together. Once I've got a good model, I've got increasing confidence that the results from that, I can use that model to replace validation that I would have previously done with test.
Right.
And a model's good because I can run many more scenarios than I'm ever going to be able to test. Mm-hmm. So this emphasis is testing is partly to test the model, all the assumptions essentially that we're using around how we've built our design.
Okay, and that's presumably that means less testing, which is often a cost, seen as a cost, right? You can make that process more efficient.
You can make it more efficient and therefore better. It's not necessarily less testing. I think most projects I've ever worked on, we would test as much as the budget allows.
Yes.
If I'm using models, I can be more focused in my testing and therefore make it more effective and more likely to find things. And with most complex systems, it's always the edge cases that are the difficult ones. Yeah. And so if I can spend more time focusing my test tasks on the things that are most likely to find defects, it's going to make it much more valuable. And as a system gets more complicated, I've got to get better at doing that as well.
Okay, that's a really interesting idea that that you can be more focused, a more focused approach. I'd just like this at this point just to introduce another concept called the digital thread. Seems like an opportune moment to do that. What's the thinking behind that?
Yeah, sure. So I suppose a word that we would always we'd recognise from most workplaces is audit. That we need to show how things have been collected together, how something has been put into service. How did it get there? Perhaps you could consider it as the provenance of that thing.
Yeah.
And it is that trace. When we talk about digital thread, it's how do we do that trace? And that trace applies just as much for a nut or a bolt or a hose or something that would go into service and knowing how it's been manufactured, what it's been made of, to lines of software in an embedded control system. They have to have this same provenance. And broadly, the term digital thread describes how do we arrive at that thing in service and what's all the evidence that we've done our job correctly.
Okay. So, and how would that relate to, taking a model-based approach to development and the digital twin? Would you find is it all linked in? That data is all within the thread, or?
It is. Think about, I suppose it would help to think about what are at the two ends of the thread. If we've got the thing, whether it's a piece of software or a hose or whatever in service, the thread takes us all the way back to what were the operational requirements for that part of that piece of the system. So we go from software, we've got to trace all the way up to something we expect, let's say, the aircraft to do, how the pilot would be expected to interact with the aircraft. And we can imagine a huge tree that follows right through the design about how we go from that overall statement about what we expect the asset, the aircraft engine, whatever, to do, and how that traces down to this is what this particular bit of software does to contribute to delivering that overall requirement. And I should say this trace is massive. Typically for some sort of avionics control box on an aircraft, we will expect there to be tens of thousands of requirements for what that software must do.
Yeah.
And of course, these are tens of thousands of requirements that have to have been correctly and completely tested at the same time.
Yeah.
So the digital thread describes how all our different engineering activities go together to demonstrate that a particular thing is fit for service.
Okay, so now engineers have these concepts and tools at their disposal. How do they? What kind of direct benefit do they get from it? Presumably it just speeds everything up, right? Or am I wrong?
It does. It speeds things up, and a bit like with our analogy with doing the testing better, if we've got good tooling and good support for how we do that testing and good models behind it, we can be more agile in our design as well. Yeah. We can consider more cases. Most projects have a finite amount of time available. And so if we are very agile in how we can go from the requirement, what something's expected to do, to how it's done, we can consider more cases. We can study the design space more widely. We can be much more confident that we haven't missed things. The worst thing that happens is when something gets assumed and is then passed on to the next stage. So we've passed a defect on to be found later on. That's really expensive. If we're sure about what we're designing and the digital thread tells us everything that we're expected to do and test, we can be confident that we're not passing defects on to the next stage. And really, this is all about, and the work that we do at Mathworks is all about trying to make that analysis of that thread as easy as possible, and that the good tooling supports the engineers doing that job as best as it possibly can. So they have to worry least about those sort of trace and documentation tasks, which I know when I used to do engineering of this type, I'd spend most of my time writing specs and test specs and things like that. If we can really automate that and make that easy, the engineers can focus on the things that they uniquely bring, which is the engineering judgment and insight.
So, of course, in aerospace, we're working towards certification all the time. I mean, how does it help us achieve that? I mean, the things we're talking about, these model-based approach, the digital thread, are they all accepted in kind of current standards and ways of working?
I'll address them separately. The answer is yes to both of them.
Yeah.
The trace, I think, in certification processes, there's two things you have to produce, and one is the evidence that you have tested everything fully. And that's what gets explicitly audited. And this is where, if you have the tooling creating that digital thread for you as you go, and you're very automated about how you move between the different stages, ultimately it's that trace evidence, it's the test result and the trace evidence are the things that you present to the authorities to demonstrate that that component has been not just thoroughly tested, but completely tested in every way that it needs to be. So that's how the digital thread helps. We then have the models, the use of models, which they are absolutely accepted as part of aerospace clearance processes, because the clearance authorities recognise that you will do a better job of testing if you've worked at that higher level, you've used some model results that have been carefully validated against real-world data. So models are an increasing part of that evidence, and they are supporting design decisions. So they're supporting decisions that you typically make early on and then validate with a test later. So it is absolutely a part of it, and the standards are explicit about how models can be used and where they can be used. And in the last 10 years or so, a lot of the main aerospace standards like DO 178 and DO 331 have done a really good job of clarifying how we can use models across all those stages of the design. Okay,
so, I mean, how are these tools really enabling the kind of next generation of aircraft, if that's not too general a question? So I'm thinking here about electrification and these new VTOL aircraft concepts that we're seeing. Do we need these to make these types of aircraft? How do they fit in?
Yeah, so if we think about the things we see at the leading edge, the main thing we'd look at them, the integration of electrical systems, more complex flight modes, they are just much more complex and much more software dependent than a single-seater light aircraft or something like that, which would have minimal software support built into its design. Yeah. So we've got these designs where both the modes of operation and the role that software provides are much, much more complicated. So as we increase that complexity, we've got to do a much better job of how do we tie everything together to demonstrate this completeness, the thing we've been discussing all along. So when you move to VTOL or more electric, the number of requirements you're trying to satisfy actually goes up. The size of this tree becomes bigger and bigger. So you want to make sure you've got tooling that's as good as possible at helping you traverse these layers, and that you're really efficient and you're maximizing automation where you can and applying engineering judgment where you can, because these things are just that much more complicated.
Mm-hmm. Okay, sure. And I mean, what's the kind of, I mean, do you need your software to achieve all of this, Mathworks software? Or, I mean, is that, could you just explain to me, and what's the kind of latest features that you're incorporating to help enable all of this that we're talking about?
Sure. So do you absolutely need the software? No, our job is to provide tools that make it as efficient as it can for an engineer to do those tasks. So you can do them without, it's going to take you longer. Yeah. We can automate the things that can be automated, the writing out of source code or the generation of trace information are two good examples. We can automate those well so that the engineers don't have to develop big paper trails or develop custom tooling to do that. We can take that job and put it in a trusted sort of pre-qualified environment. The areas that really impacts some of this, I think, is around how do we provide modelling components that allow you to build these physics models we were talking about earlier? Yeah. How do we support the work that systems engineers are doing, considering the trade-offs? This is a big investment area for us at the moment, that the systems and the design and the implementation are often very separate in the organisations we work with, and we're trying to bring their work together as much as possible. So if we can get these teams working in a more multidisciplinary way, in a common environment, effectively supported by mathematics, that gives them a common language so that they can discuss trade-offs, compromises, etc., and do the design much better and have a well-defined thing that they can then go and test. So we think about it's all about automation. It's all about providing this tied together environment that works at all these different stages of the design process.
Okay, great. Thanks, Mark. I think just one more question from me, and that's, I mean, is there a case study or an example, recent example that you could point to that you think is a particularly good application of maybe a digital twin or a digital thread that approach that you think it's worth, that illustrates what we've been discussing? Or
we are increasingly trying to make these examples as available as possible. So there is a good example on a thing our File Exchange, which is a place where we publish reference examples, doing predictive maintenance on a hydraulic pump. Okay. So it's a relatively simple piece of hardware, backed by a physics model, and using the machine learning techniques that I was talking about earlier. So I'll send a link to that afterwards. Yeah. And I also think it's interesting to hear perhaps not what I say about how our tools are used, but what our customers say. So I've also got a link to a presentation that was given at one of our, back in the days when we could all have big conferences together, at our last big conference in the UK called MATLAB Expo, which is Matt Lay, who's at the time was the head of systems and software for Rolls-Royce. He talks about how his team have been impacted by the adoption of these techniques and what they're now able to do in some of these emerging areas, such as electric aircraft design. So there's some really good testimonies in that. It's a video, but I'll send you a link afterwards of how it's impacted his team and how they feel they can be more productive as engineers because of the tooling that's supporting them now.
Perfect. Sounds good, Mark. Thank you. I will include those links in the description of the podcast for listeners to follow up on. I don't know if there's anything else that you'd like to add, Mark, here at this point, but it's been an interesting chat, and it's good to, at least for my benefit, to hear about to have these kind of concepts and this process explained to me.
Cool. I'd just like to say these are exciting times. There's lots of really good cutting-edge engineering being done out there, and increasingly having the tools supporting them means that people can do lots of amazing stuff and make sort of achievements that 10, 20 years ago we just wouldn't have thought would be possible. So, been interesting talking to you. Thanks very much, Ben.
Thanks, Mark. Thanks again for your time. Okay, so that was Mark Walker from Mathworks with some really interesting thoughts on how software tools like MATLAB and SIMULINK are integral to developing the complex systems that are at the heart of today's aircraft and increasingly future generations of aircraft. So I hope you can join me for the next podcast, which will be a chat with Mark Henning, who is Managing Director of an eVTOL developer called Autoflight Europe, which, like many eVTOL aircraft developers, is targeting a 2025 entry into service for its aircraft. So please subscribe to make sure you don't miss it. Plus, there's a bank of all the previous podcasts at aerospace-testing-international.com/podcasts, should you want to listen to any of those. So thanks for your attention and have a great day.